In this video, we want to consider what happens when we are multiplying by fractions, or simply multiplying multiple fractions together. So we'll entitle this Multiplying Fractions. So for our first example, let's consider 2/3 times 5. In order to understand this, let's make sure we review a little bit about multiplication. If I had 5 blocks here, this could be represented, since it's 5 tall and 1 wide, this would be 1 times 5. If I were to take a second set of blocks, we're now at 2 times 5, and if you count them up and ignore the squiggles in my lines, you would get 10. And if I were to continue on, this would be 3 sets of 5, or 3 times 5, which would give us 15. So what would the meaning of 2/3 times 5 be? Well, 2/3 is between 0 and 1 in terms of integers. So what that would mean is we haven't yet counted a set of 5 once. We've taken 2/3 of a set of 5, and if I want to draw that in, that would be 2/3 wide and 5 units tall. Let me draw a vertical line carefully all the way up to the top. Okay, so there we have a region that we can shade in lightly here, and let's consider what this looks like geometrically. We have each one of these parts that's shaded in, that would be a block that is 2/3 of a unit in size. This would also be 2/3 of a unit, and then we'd have another 2/3 of a unit, and then we would have 2/3 of a unit again, and 2/3 of a unit again. We could say that 2/3 times 5 is equivalent to adding 2/3 5 times. I write it out longhand, that's what it would look like. We know mathematically we would prefer to write 5 times 2/3, or 5 times 2/3, like that. Now, adding up 2/3 5 times, since they're all thirds, they have the same denominator, we can take 2 plus 2 plus 2 plus 2 plus 2, and that would give us 10 of them. So we have 10 1/3, also known as 10/3, as our answer. Well, what are other geometric ways that we could look at 2/3 times 5? To get the same amount of area, we could have taken 5 units, and let me do this right here. And rather than taking a width of 2/3, let's consider what happens if we take twice 5. Okay, so we have a block that looks like this. Now, obviously, twice 5 is not going to give us the same answer. That's going to be 10. But let's consider what happens if we cut that in a third. So let's divide 5 into thirds here. So it looks like if we were to divide 5 into thirds, we could put hash marks in those locations. So I have 2 times 5, and I'm now going to divide it in a third. And let's see what we have here. Okay, so if I wanted to divide 5 by 3, what would the height of each one of these be? It would end up being 1 plus 2/3. If you take 5 divided by 3, you have 5/3, which would be 1 plus 2/3. So how much area do we have? We have 1, another 1, but then each one of these must be 2/3 plus another 2/3, okay? So let's go back up. 10/3 would have been 3 and 1/3. What do we have here? We have, I'm going to do this to the left, we have 1 plus 1 plus 2/3 plus 2/3. Okay, so if we add that up, we have 2 plus 4/3. Since 4/3 is 1 1/3, we can say that that is 3 and 1/3. Notice we got exactly the same area. So we could have multiplied 2 times 5 and then turned around and divided by 3, or we could say that's 2 times 5. Instead of dividing by 3, we could multiply by 1/3. So that's another way that we could look at this problem. Another thing we could have done is we could have started with 5 blocks. Like before. And we could first have divided that by a third. Okay, divide that into thirds, I should say. And so we could put a line right here, and we could divide it by a third. And then after dividing that in a third, we could double the amount we have, which would put us out here. Or we could double the amount by going up. So this would have been 1 2/3. You can see the first thing that I drew would actually look exactly the same as the area that we have to the left. But if I go 1 2/3 and then I go up another 2/3 and another 1, I will be up here. Let me go up one more block, would have been up here, and we would be up to here. Okay, so this would be another 1 2/3. And we had 1 2/3 down here. So what is our total height? If we had 1 2/3 twice, we end up with a height of 10/3, and we had a width that had been 1. So once again, this would come out to an area. Let's consider this region right here. This region right here has a height of 10/3 and a width of 1. So its area is also 10/3. So note what we did this time. This time we took 5 and we divided it by 3, and then we multiplied that by 2. We could consider that to be 5 times 1/3. That would be the same as dividing by 3, taking 1/3 of 5, and then multiplying by 2. So what we really need to note here is that we have done many different things. The first thing that we did was we simply took 2/3 as the width and multiplied by a height as 5. The second thing that we did was we took 2 times, well, let me box this one in. We took twice 5 and then divided by 3. The third thing we did was we took 1/3 of 5, or divided 5 by 3, and then multiplied by 2. Clearly, this illustrates that we have a commutative property going on here. So let me clear the ink. So quickly, 2/3 times 5 could be expressed a lot of different ways. We could consider it to be, simply leave it as 2/3 times 5. We could consider it to be 2 times 5 divided by 3, where we have associated the 2 and the 5. Or we saw that we could consider that this would be twice 1/3 of 5. They are all the same. The important thing here is to realize that this could be written as 2 times 1/3 times 5, and we can apply the commutative property of multiplication and do this several different ways. Okay, so the second way down here would be taking the 2 times the 5 first and then dividing by the 3, so we have switched the order and associated things differently. And in this case, we have actually associated the 1/3 with the 5 right away and then multiplied by the 2. So we can do things in any order that we choose when we have strictly multiplication and division going on. So let's consider another problem. Let's consider the problem 2/3 times 9/10. So now we have two fractions. I'm going to rewrite this as 1 times 2 times 1/3, which would be the same as dividing by 3, times 9 times 1/10, which would be the same as multiplying by a tenth is the same as dividing by 10. So we have all of these things going on. Why did I write the 1 first? We can think of the original problem as having the 1 unit, and we have to do 4 different things to it. We have to multiply by 2, we have to divide by 3, we have to multiply by 9, and we have to divide by 10. Thinking of the divisions as multiplications of reciprocals will be nice. So instead of dividing by 3, multiplying by 1/3, instead of dividing by 10, multiplying by 1/10, we have 5 factors here, including 1 as one of them, and we can multiply them in any order. So if we can multiply them in any order, it's good to look for patterns. If I were to be taking 1/3 of something, I would really like to be taking 1/3 of 9, or dividing 9 by 3, instead of dividing the 2 by the 3. And we would like to be able to group the 2 and the 10. So we can rewrite this problem as we don't have to multiply by 1 or show the multiplication by 1 as 2/10 times 9/3. Now I think it might be clear why we would like to do something like that. We can now use the multiplicative identity. We can take both the numerator and the denominator of the second factor, 9/3, and we could multiply both of them by 1/3. We could take the numerator and denominator of the first factor and multiply both of those by 1/2. Okay. So really what we have done here is we have 1/2 over 1/2 is really multiplying by 1. 1/3 divided by 1/3 is really multiplying by 1. But now if we multiply those things out, 1/2 times 2 is 1. 1/2 times 10 is 5. 1/3 times 9 is 3. And 1/3 times 3 is 1. So we're left with a final answer of 3/5. Now, in the long run, you'll do this in a much faster way. You won't move everything around and rewrite the problem and show the multiplicative identities. So you may have solved problems involving multiplication by fractions in a way that looks more like this. You right away, it's implied that you're associating the 3 and the 9. And since 9 divided by 3, we can divide both of those by 3, and we can say, well, 3 divided by 3 is 1, and 9 divided by 3 is 3. Now we can turn around and do a similar thing with the 2 and the 10. We can associate those, and they're both divisible by 2. So if we divide the numerator by 2, we're left with 1, and if we divide the denominator by 2, we're left with 5. Note we divided both things by 2, so we're really doing exactly what we had over here and using the multiplicative identity. We're multiplying by 1/2 over 1/2 when we divide both numerator and denominator by 2. And after doing all of the crossing out that we had there, we realize we have 1 times 3 left in the numerator, which is 3, and we have 1 times 5 in the denominator, which gives us 5. So this is a shorthand way of accomplishing what we have on the left, but what we have on the left is really showing all of the intricacies of what we're doing. We are using the commutative property to move the numbers around, we're using the associative property to group them, and then we're using the multiplicative identity in order to simplify the problem. Now let me just note a couple of things about multiplication. Multiplication is not addition. I think that's fairly obvious. In fact, multiplication is much easier. When we add things, they must be like each other. So when we're dealing with fractions, you must add halves to halves and thirds to thirds. So to add things, they must be, let me make my A look like an A. To add things, they must be like each other. So if I have something like 2/3 plus 9/10, we can't just add them up. We won't go through it now, but we would need to find a least common denominator, which would be 30 in this case, and use the multiplicative identity in order to allow us to add. But to multiply, we don't need to worry about that at all. We can take 2/3 times 9/10, and we can simply say that that is 18 out of 30. We could have simplified that by realizing that 2 and 10 could have been associated, or we can simplify it now and divide both the numerator and denominator by 2 and get that the answer is 9/15. What is the meaning of this? 2/3 times 9/10 we can think of as an area again. So 2/3 would be a height of 2/3, about like that, and 9/10 would be a width that's almost but not quite 1. So we can take 2/3 times 9/10 and we can get an area of 9/15. The two sides do not have to have similar fractions in them when we're multiplying. You can get an area without getting a common denominator. But if we wanted to add the lengths of the sides and find a half of a perimeter by adding this length to this length, we would be doing the addition problem. And if we're doing the addition problem, we would need to have a common denominator.